We spent a lot of time going over our previous sets of questions and problems today in class. I don't think we can take as much time to go over the questions we did at the end, so I'm making this video to go through them. Okay. Our first question is ranking the electric fields in terms of their magnitude. So we might at first be tempted to just plug in and do all the calculations with using just the magnitude of the charge. But it turns out that we could just do really the equivalent of Q over R squared to do the ranking. And we also could ignore the microcoulombs, and we could keep the R in centimeters since the charges are all measured in microcoulombs and the distances are all measured in centimeters. So doing that, I'm getting these values that I'm going to compare. For A, it's proportional to 20 over 4 squared, which is 16, which is 1.25. For the field described in part B, our charge is 10. Remember, we're using magnitude, so we're going to ignore the negative sign. 3 squared is 9, so that's 1.11. For C, we'll use 8 for the charge. We'll square 2 and get 4. That gives us 2. And finally, for D, we have 5 over 1 squared, and that is just 5. So we say D becomes the biggest from that. Next we have C. Next we have A. And finally B is the smallest. So that is our ranking. Now this question is a little tricky, but it's similar to the examples we did in class today, except for the fact that we're looking for electric field and not force. Also notice that it said that our charges, obviously they're trying to tell us something with the little q and the big Q. It's giving you a sense of their magnitude, but it does mention that they're of opposite signs. In order to answer your question, you could just assign them signs. Once you do it with the signs that you assigned the first time, you should be able to convince yourself that switching the signs would not really change your answer. I'm going to just call the little charge 1 and the big charge 2 because I want to label the electric fields in my 3 regions, and I want to be able to remember which field is coming from which charge. So we are trying to figure out where the electric field would cancel in region X, Y, or Z, which means we need electric fields to be in opposite directions. But we also need them to have equal magnitude. I'm going to start in region X. And first think about what would be the electric field due to charge 1 in that area, because negative charges have electric fields that point towards them. E1 would look like this. It would point to the right. The electric field due to big charge Q, that one was a positive charge, so its electric field points away from it, so E2 points to the left. So X looks like that's a possible area. We'll come back to that. Let's just do all the regions first. When I do region Y, the electric field due to charge 1 is towards it, and the electric field due to charge 2 is away from it, and that gives me 2 fields in the same direction. So Y is never going to be my region. Finally, we will do Z. The electric field due to charge 1 is towards it, so that's going to be to the left. The electric field due to charge 2 is away from it. That will be to the right. So now I see that the fields are in opposite directions in X and Z, but we also have to ask ourselves, would they be in equal magnitude? keep in mind that the charge has something to do with how strong the electric field is. And in region Z, E2 will be much stronger than E1 because this is due to big charge and we're closer to it. This one is due to the little charge and we're far away. So all around, there's no way that E1 can be equal in magnitude to E2. But in region X, we're far away from big Q and we're close to little q, so that these two fields have a possibility of being equal to each other. And so that leads us to our answer to be region X. All right, we have our triangles again, except now we see that there isn't a charge at point P. This is often the case when we're asked to find the electric field. We're going to be asked to find it at a location that there's no charge there, because charges create electric fields in the space around them. We don't have to be looking on a charge. So if I want to figure out the answer to what is the total electric field at point P, I can say charge 1 creates an electric field in this direction because it wants to have an electric field towards it. E2, charge 2 is a positive charge, so it creates an electric field going away from it. The magnitude of E1 and E2 are the same because it's the same magnitude of charge and same distance. So our total electric field, because of symmetry, will be directly up. And so that is our answer for that question. Now they ask us to actually do a calculation. So I'm just going to rewrite these, just relabel them, just to remind us. Now I draw the vectors first, then I figure out how big they are. E1 and E2 have the same magnitude. And they are the same distance. They have the same magnitude of charge, same distance away. The R is 15 centimeters. And if we do the calculation, we find that this is about 2,000 newtons per coulomb is the units for electric field. Because of symmetry, E total X is 0, so E total is in the Y direction. E total Y is equal to E1Y plus E2Y, but that could also be written as 2E1Y because they will have the same Y component. If I wanted to write the Y components, I have a choice of what angles I can use. I'm going to stick with the Y component, the 30-degree angle. And so the Y component will be found by taking 2, because I had a contribution from E1 and E2, times E1, which is 2,000, times the sine of 30, which actually gives me a total of 2,000 newtons per coulomb directly up, and that is my total electric field. The next couple questions are about charge, distributions of charge, and I know that this material seems a lot more confusing and it could cause some anxiety. We just want to kind of show you how you can do the calculations to find the electric field due to these distributions. you're not expected to be able to replicate the integration that's done. Maybe be familiar with the final expressions and be able to, plug numbers in and stuff, but you're not going to have to do any integration. Part of the reason that we do this is because in the next chapter we'll use Gauss's law and we'll find much easier ways to do this calculation. So in this question, we have two infinite plane sheets with uniform charge densities of equal magnitude and opposite sign are placed parallel to each other and separated by a distance d. In the region between the sheets, where does the local electric field have the greatest magnitude? I kind of feel like this is a little bit of a trick question. What we find in the chapter is the electric field due to one sheet of charge is sigma over 2 epsilon naught. Sigma is the charge density in this case because the charge is distributed over an area. It is charge per unit area. So in this question here, each of these sheets are creating their own electric fields around them with those magnitudes. The arrows I drew are the positive sheet creates electric fields in these directions. The negative sheet creates fields in those directions. Each one of them have a magnitude of sigma over 2 epsilon naught. We can see in the middle. They would add, and you get sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So that gives you sigma over epsilon naught. So this is between the plates. One of the things that we learn in our reading is that these fields are uniform. We don't really talk about them dropping off as we go away. So technically, the field would be the strongest halfway between the two sheets, but honestly, it would be anywhere between the two sheets. It should have this final magnitude. This problem helps us think a little bit about the fact of what we're doing when we're creating, integrating electric field. To find the total electric field, we integrate little increments of it, which are caused by little pieces of charge. So right here, I have a dq. And if this is a positive charge, it's creating an electric field pointing away from it. So this is its contribution of the electric field is in this direction. If we go all around the semicircle, we get similar contributions, but we should see that there's a certain degree of symmetry, so that as we add all the small contributions, the EX cancel, because for every if this electric field right here has an X component and a Y component, there would be an electric field over in this direction that has an X component in the opposite direction, but a Y component in the same direction. So what happens is as I go around the semicircle, the X components cancel out and I'm only left with the Y components. And so the electric field that's left after I go all the way around will be in the minus Y direction. Finally, the last one talks about how we would find the electric field due to a segment of a wire. but we actually have an expression. And see here, we also have sort of the x components cancel. And we only get an EZ when we go all the way along this little segment of wire that has charge. The charge here is charge per unit length, and we use lambda. So yes, we're reusing lambda. The expression we get, because they go through the integration in your book and come up with an expression, and we actually can use the expression here, so it becomes basically a plug and chug problem, so I'm not that nuts about it. This is the equation that we have for our particular problem. L is 0.5 meters. Lambda times L would be the total charge, which would be 6 microcoulombs, or 6 times 10 to the minus 6 coulombs. And our Z value is 25 centimeters, or 0.25 meters. And so we would plug in to that equation, 9 times 10 to the 9th, 6 microcoulombs, 0.25 times square root of 0.25 squared, plus 0.5 squared over 4. All that was under the square root. I did the calculation. If I did it right, it was 6.11 times 10 to the 5th newtons per coulomb. I'm not going to swear that I didn't make a little math mistake there, but hopefully not. So these are the problems. You should have worked through them on your own, but now you can kind of go through, check your work, and make sure you understand.